So today we're going to take a look at this topic titled the Lagrange form of the remainder. And the essential question we're going to talk about today is how good is our Taylor polynomial approximation? So we spent the other day creating Taylor polynomials to represent and to approximate functions by matching their defined values and multiple derivatives at a singular point, which we called the center. But how good is that approximation? The Lagrange form of the remainder will give us an upper bound or an absolute maximum error, or the absolute maximum amount that we could be off by to kind of gauge our accuracy. So to start off with, let's just review by creating a Taylor polynomial. So for the function natural log of x, let's use a third degree Taylor polynomial centered at 1 to approximate f of 1.5. So if I'm going to create a Taylor polynomial through a third degree, I need the first three derivatives. So the first derivative is going to be 1 over x. The second derivative will be negative 1 over x squared. And the third derivative will be positive 2 over x cubed. All right, so our coefficients, a of 0 is just going to be the natural log of 1, which is 0. A of 1, which is going to be our first derivative, evaluated at the center, which is 1, divided by 1 factorial. F prime of 1 is 1, so 1 over 1 is going to be 1. And so let's just do the next few. A of 2 will be the value of our second derivative, which is going to be negative 1 over 2 factorial, which is negative 1/2. And finally, a of 3 is going to be the value of our third derivative at 1 at our center, which is 2 over 3 factorial. So let's see, that's 2 over 6, 1/3. So our polynomial then, so I'll call it T sub 3, our third degree Taylor polynomial, just in general, is going to be 1/3 x minus 1 cubed. Don't forget that it's x minus c, not just x, minus 1/2 x minus 1 squared plus 1 x minus 1 to the first power plus 0. So we go ahead and plug in 1.5 for our x value, and let's see what our approximation is. And if you type in 1.5 into that polynomial up above, you get 0.4166 repeating. So that is our approximation. So the question is, how good is this approximation? That's what we'll take a look at next. All right, so how good is our approximation? Well, just a couple of kind of vocabulary terms here. We can always think of our function. So f is the actual function we're trying to represent. We're approximating it with a Taylor polynomial, which is the t piece, using some number of degrees, which is the little sub n. So we could use a second degree, a third degree, an 18th degree polynomial, but it's still an approximation, and it's going to be off by a little bit. And that off, this is our r, so this is our remainder. This is how far off we are. This is our approximation, and f is kind of our real value, if you will. So you're going to hear me use the word error and remainder interchangeably. The error is the absolute value of our remainder. So it could be, the absolute value just means that the value could be bigger or smaller by that amount. And the important part, at least for me, is recognizing that remainder is just the difference between the real value minus the approximation. That's how far off we are, or thus our error. All right, so what we're going to use for our error is the Lagrange form of the remainder. This formula looks really complicated, but it's really not. What I want you to see is that essentially this is just really the n plus 1 term. If I were to ask you to do another Taylor polynomial, or take the first example we did, and rather than go 3 degrees, go 4, if you want one more, well, what would you do? You would take the next derivative, which would be the n plus 1 derivative, and you'd plug in the center. So we'll talk about what z is here in just a bit, but you'd plug in the center, but everything else would be the same. You would divide by the next factorial, so the n plus 1 factorial, and you'd take your x minus c, your x minus your center, and you'd raise it to the next power. To help make this a little easier to remember, the basic form of this is going to be just the next term, very similar to what we did with alternating series. The remainder was the next term after we stopped adding. Now, what is z? So z is a value between x and c. So this is the value between x and c. So remember that x is the value that we're trying to approximate. So in our first example, it was 1.5, and c is our center. So in our first example, c was 1. So z is going to represent some value between 1 and 1.5. And what this says right here is that we can actually find a value z that exists every time between 1 and 1.5 that would give us the remainder exactly. It's going to equal the remainder. So that's good. The hard part is that finding z, finding that exact value that equals our remainder, is incredibly difficult. So we're not going to do that. We're not going to find the exact value for z, so we're not going to find the exact remainder. But what we're going to do is we're going to find a way to maximize this thing so that we can at least create an upper ceiling or an upper bound for our error. And this is what it's going to look like. We're going to say that the absolute value of our remainder using n degrees for a value x is going to be smaller than or equal to, well, I'm going to pause here for a second and ignore the f of n plus 1 piece. Ignore the derivative piece for a second. Notice that everything else, the n minus 1, this is a constant, right? Because we know that we know what n is, and so we're going to use the next value. If we go from n, we go from n plus 1 factorial. We know what we're trying to approximate at, so we would know x. We would know the center, and like I mentioned before, we know what n is. Everything I have written in blue would be a constant. It would be given to you in the problem. What you wouldn't know is the value of z. That's the problem. That's where we're getting stuck. And so to make sure that we have the ultimate highest, what we're going to do is we're going to maximize that derivative. So we're going to calculate the maximum of the n plus 1 derivative for z. So we're going to figure out in our last case what value between 1 and 1.5, which were the z values in the first example, would maximize the next derivative. And we'll walk through that here in just a second. And the last thing I want to add to this rule is that we're going to put absolute values on the derivative just to make sure that we get the ultimate biggest number. For example, if we had a value ranges from -1 to -3, we would want to use the -3, or when I take it, the absolute value of it, 3, just to ensure that I get the largest value possible. So we just put absolute values on there, similar to how there's absolute values here, just to keep everything positive and as big as possible to ensure we have our upper bound. So let's take a look at our first example. So from the first example, let's say this is part B. Use the Lagrange form to obtain an upper bound for the error on our approximation. So from our first example, we found that t of 3 evaluated at 1.5 was 0.416 repeating. That was our approximation. So I want to know, at most, how far off is this from our real value? Well, let's go ahead and use our new Lagrange form, which says that the absolute value of our remainder using a third-degree polynomial and approximating the value when x is 1.5, that'll be less than or equal to, I'm going to hold off on the top piece. This bottom piece is n plus 1. So we know n is 3. That's what I was referring to earlier, and that we would know how many degrees we'd be using. So that would be 3 plus 1, or 4, factorial. This is x minus c. X is what we're approximating, which is 1.5. C is our center, which is 1, evaluated at the n plus 1 power, which we know what n is. So let's put that in there. 3 plus 1, so again to be raised to the 4th power, our next term. And now in here we want to maximize the absolute value of the next derivative, which would be the 4th derivative, for all possible values of z. So in our case here, z is going to be between our center and the value of x that we're trying to approximate, so 1 to 1.5. Okay, so this is kind of like an absolute maximum problem. Well, let's get the 4th derivative. And so using our previous work, our 4th derivative of the natural log, well, this derivative is going to be negative 6 over x to the 4th. All right, and so we want to find that what's the maximum value of that 4th derivative over the interval 1 to 1.5. Well, first of all, note that we're taking the absolute value of it, so this negative is just going to go positive, so we don't have to worry about that. 6 divided by x to the 4th. Well, this is going to be a decreasing function because our denominator just continues to get bigger and bigger as x's grow. So I have a decreasing function from 1 to 1.5. So when am I going to have the biggest value? Well, that's going to be at the beginning of the interval before it continues to decrease. So our absolute maximum value is going to be when x is 1. So I'm going to put maximum value would be when I plug in 1. So 6 over 1 to the 4th, our maximum value is 6. Okay, so this is all kind of side work here. So to finish this problem off, I know that the absolute value of r of 3, evaluated at 1.5, will be less than or equal to 6 divided by 4 factorial times 1.5 minus 1 would be 0.5 to the 4th power. If you were to type that into your calculator, let's see what decimal we would get. If you were to type this in your calculator, you would get that the remainder at most will be less than 0.015625. So I know at the very, very least, our approximation right here, 0.4166, is within 0.015625 of the actual answer. And just for just to check, since we do have a calculator and I can figure out what the actual value is, and I invite you to do this with me, the actual value, the natural log of 1.5, and I'm going to create a little bit of room for me over here. Well, maybe not. Won't let me erase, but that's fine. Oh, wait, I can outthink it. If I create some space over here for a second, I just want to kind of check to see what we've just done together. On my calculator, the natural log, that was too thick. All right, try this again. The natural log of 1.5 is 0.405465181. So if I were to subtract my actual value from my approximated value and take the absolute value, we would get 0.011201. This right here is the actual error. That's actually how far off we are. But what I want you to note is that it is definitely smaller than 0.015. So we found that at most we're going to be off by 0.0156. We were actually off by 0.011. The reason we don't do it this way is because the problems that we're going to see on the AP exam, we're not going to actually know what the function actually is. Or we're not going to have a calculator to be able to figure out what the natural log of 1.5 is. But I just want to go through that last bit just to show you that we calculated with the Lagrange form that at most we're going to be off by 0.015, when in reality, since we were able to check our work, we were off by 0.011. All right, so let's do one more just to practice what we've learned. So let t of 5, let the 5th degree Taylor polynomial evaluated at 1 be just that, the 5th degree Taylor polynomial for the function e to the x centered at 0. use the Lagrange form of the remainder to obtain an upper bound for our approximation. So I just need the upper bound of the approximation. I don't need to actually find the approximation itself. So the Lagrange form of the approximation says that the absolute value of our approximation, which is a 5th degree polynomial evaluating 1, will be less than or equal to the next term. So we're going to maximize the absolute value of the next derivative, which would be the 6th derivative for some value z, over 6 factorial times x, which is 1, minus our center, which is 0, to the next power, which is still 6. So 6 factorial, we can use our calculator to get 1 minus 0 to the 6th power. That's just 1. Our focus is, let's maximize this 6th derivative. So f is e to the x. So what's the 6th derivative of e to the x? Well, luckily, e to the x's derivative is always itself. So the 6th derivative is e to the x, and I want to maximize it for z. Remember that z are all the values between our center and the value of x that we're approximating. So our center is 0. We're trying to approximate 1. So z is representing all the numbers over the interval 0 to 1. So for e to the x, when does it have its maximum value? Well, e to the x is an increasing function, so its maximum value will be at 1, at the right end of the interval, so e to the 1, or e. So this inequality, or this remainder, will be less than or equal to the maximum of the 6th derivative, which was e, divided by 6 factorial times, remember this is just 1, so we won't worry about that. Let's go ahead and type that into our calculator, e divided by 6 factorial, and you get 0.00377. So I would know that if I were to create a 5th degree Taylor polynomial for e to the x centered at 0 and plug 1 into it, the value that I get is going to be within 0.00377 of the actual value of our function at 1. All right, this will be our last example, and it's very similar, but it's just going to switch things around. In this problem, they give me the maximum error that I want, and it wants me to figure out how many degrees would I need to take out my Taylor polynomial so that I achieve that level of accuracy. So let's let t of n be a Taylor polynomial that has n degrees, and it's going to represent the function for the function of cosine of x, and we'll center it at 0. So determine the degree of the Taylor polynomial. So the error, when I plug in 0.1, is less than 0.001. Okay, so let's kind of just start there. We know that, or we want the absolute value of our r using some number of degrees. We don't know n at this point, but we're going to plug in 0.1. The Taylor form tells me that that's always going to be less than or equal to the maximum of the absolute value of our n plus 1 derivative, evaluated at z, divided by n plus 1 factorial times x, which we do know, 0.1, minus our center, which is 0, to the n plus 1 power. So in this case, we actually don't know what the degrees are, so unfortunately we're not going to be able to fill in anything with n. But we do know x and we do know c. And this is going to be our error, and I need this piece right here. This needs to be less than 0.001. I need to make sure that I pick an n value so that that is for sure less than 0.001. How do we solve that? Well, this is going to be good news or bad news. Unfortunately, we can't actually solve this conveniently because I don't even know what derivative to use. If I use a 2nd degree polynomial, I'll need to check out the 3rd derivative and maximize that. And if I want to take a look at the 7th degree polynomial, I would need the next derivative, which would be the 8th. And what function am I dealing with? I'm dealing with cosine, and its derivatives are not the same. If it were e to the x, I could actually solve it exactly because all of their derivatives are the same, and that would make it really nice and convenient. Unfortunately, that's not the case here. So we're just going to do trial and error and just go until we actually reach our level of accuracy. So let's say n is 1. What would happen if n is 1? Well, I'd have the maximum of the absolute value of the second derivative evaluated at z divided by 2 factorial times 0.1 raised to the second power. Okay, well, what's the second derivative? Well, cosine is f. F prime would be negative sine. So f double prime, this is going to be negative cosine of x. So absolute value, I don't care about the negative sign. And what are my values for z? Well, z is going to consist of the interval from my center, which is 0, to what I'm trying to approximate, which is 0.1. Well, cosine has its maximum value at 0 when it has a value of 1. So this boils down to 1 over 2 factorial times 0.1 squared. If you were to type that into your calculator, 1/2 times 0.1 squared, you get 0.005. Close, but it needs to be less than 0.001, so still too big. So let's go to the next one. What if n were 2? What if I created a quadratic, a second degree Taylor polynomial, centered at 0 for cosine? Well, I would have the maximum of the next derivative, which would be the third derivative, absolute values, evaluated at z, divided by 3 factorial 0.1 cubed. Remember that 0.1 is still the 0.1 minus 0. What's the third derivative? Well, the next derivative would be sine of x. And from 0 to 0.1, sine is increasing, so sine will have its largest value at 0.1. So this becomes sine of 0.1 divided by 3 factorial, which is 6, times 0.1 cubed. And if I were to type that into my calculator, sine of 0.1 divided by 6 times 0.1 cubed, I get, and I think I can put it right here, 1.663 times 10 to the negative 5th, which is well within my desired accuracy. It's well underneath, or it is smaller than 0.001. So in this case here, I would need to create a second degree Taylor polynomial centered at 0 for cosine if I wanted my approximation at 0.1 to be less than 0.001.